Hello everyone. Today we're going to learn a little bit about the periodic table, how it is arranged, and where we can find certain groupings on it. A brief history of our modern periodic table. The first periodic table that was recorded that we are aware of was created by a gentleman named Dmitry Mendeleev. He organized his periodic table by first ordering the elements in order of increasing atomic mass, and then breaking them into columns using their oxide ratios. There were blanks left behind in this periodic table because Mendeleev predicted that there were elements that had yet to be discovered who would fill in those missing gaps. By doing so, there were a lot of patterns that were made visible. However, it was not perfect. In order to fix Mendeleev's periodic table, we had to switch from them being in order of atomic mass to being in order of atomic number. This was done by an English gentleman named Henry Moseley. This fixed a couple of strange problems that had popped up, most notably tellurium and iodine, who have the opposite pattern for atomic mass and atomic number, weren't quite in the right position, but by putting them in order of atomic number, their properties were made more consistent with nearby elements on the table. So, our modern periodic table looks as shown below. The rows, also known as periods, go across the periodic table. There are 7 periods on our periodic table as of now, with theoretically an 8th one being available if we continue to make more man-made elements. The columns are known as groups or families. They are generally called families because those who are in the same column often have similar properties in common with each other. There are 18 groups or families on the periodic table. You'll also notice there are 2 unusual rows at the bottom. They are simply moved outside of their usual place on the periodic table because otherwise the periodic table will become too lengthy to print on a piece of paper and become a little bit difficult to use. So let's talk about some important groupings on the periodic table. The first is to discuss metals, nonmetals, and metalloids. Metals are located to the left of the staircase. There is a diagonal staircase that cuts across groups 13 through 18, highlighted on the periodic table on the screen by the elements who are in olive green color. Metals are everything that is to the left, so all of groups 1 through 12, and the bottom left corner of groups 13 through 17. This does include the 2 unusual rows that are at the bottom of the periodic table. You will notice this means that most elements are in fact metals. One exception to this position rule is of course hydrogen, because hydrogen is just strange. Nonmetals are those who are to the right of this zigzag line or staircase. So these are those in the upper right corner from groups 13 through 18. There are also metalloids, those who touch the staircase. The metalloids were the ones shown in olive green on the periodic table that is on this screen. There are only a few of them: boron, silicon, germanium, arsenic, antimony, tellurium, and astatine. The distinction between the metals, nonmetals, and metalloids is based on a couple of important properties that these elements have. The first one that is important for metals is luster, which is a fancy way of saying they are shiny. Metals are also conductive of both heat and electricity. Because of their structure, which we'll learn about later on, they are able to allow electrons and heat to flow through them very easily and thus can conduct them very well. Metals are also malleable and ductile. They are very flexible in their structure. Malleable means to be able to be hammered into a thin sheet, while ductile is to be able to be drawn into a thin wire. Because of their flexibility, when you put stress on them in some way, they will change their shape rather than break their shape. All these properties are contrasted in nonmetals. Nonmetals are not lustrous. They are insulators, which are the opposite of conductors, and they are very brittle, which means they are neither malleable nor ductile. Metalloids, as the in-between, often have a mix of these properties. For example, silicon, the most common metalloid on Earth, is lustrous and conductive, like a metal, but brittle, like a nonmetal. Another set of important groupings are the blocks. The blocks are named based on the electron configurations, specifically how the electron configuration for an element ends. The S block are groups 1 and 2 of the periodic table. The P block are groups 13 through 18, with the exception of helium. The D block are groups 3 through 12 in the middle, and the F block are those two unusual rows that are found at the bottom of the periodic table. Again, these are named based on how the electron configurations end for the elements. For example, zinc, a member of a D block, element atomic number 30, is part of the D block because its final configuration ends with 3D10, with everything else coming before 3D also being filled. Let us move on to some important key families and learn about some of their properties. The first of these is group 1 of the periodic tables, the alkali metals, minus hydrogen. So these are lithium, sodium, potassium, rubidium, cesium, and also francium. The metals found in group 1 are exceptionally reactive. They react immediately when thrown into water and rather explosively, as shown in the picture here, because they produce hydrogen gas when they react with water. They also react rapidly with air and oxidize. It is very difficult to find these metals in their natural state. All of this is because alkali metals have one valence electron. A valence electron are the electrons that are on the outside for an electron configuration. Because of this, they often form +1 cations. Alkali metals like to kick off that one single valence electron in order to go down to a more stable core. Alkali metals, if you manage to find them in nature, are soft and silvery. They are so soft that you could cut them with a butter knife. Next door to the alkali metals are the alkaline earth metals, the members of group 2. These are also moderately reactive. You don't traditionally find them in their natural state in nature. However, you can still occasionally find them in the lab and don't require that much special storage, unlike the alkali metals. The alkaline earth metals have two valence or outside electrons, and, like the alkali metals, like to give away these electrons in order to go down to a more stable core when they form an ion. Thus, the alkaline earth metals like to form +2 cations. The alkaline earth metals are much harder and more dense than their neighboring alkali metals. Our next family we should look at is group 13, also known as boron's family. Their chemistry varies quite a bit, as does their metallic character throughout this family. And so our primary thing we should discuss here is that boron's family have 3 electrons each. This means that they will often form a +3 cation when they take their ion form. There are a few members of this family who can also sometimes take a +1 cation form. However, this +1 cation is more rare than the +3 is. Similarly, for carbon's family, we should discuss what is going on with the valence electrons and the common charges for carbon's family, or group 14. Carbon's family have 4 valence electrons. Because of this, they are able to form either a +4 cation or a -4 anion. They can go technically either way in order to get to a more stable number. There are a few of them, notably tin and lead, who are able to form +2 cations as well. However, these are reserved for tin and lead and are less common than +4 or -4 are. Nitrogen's family, or group 15, have 5 valence electrons each. This means that they will form -3 anions in order to gain 3 more and achieve a total set of 8 valence electrons in their ion form. This 8 is considered a stable number. Because of this, there is a rule known as the octet rule. You will notice that generally, most of the common ions listed here are so that the element will obey the octet rule. Oxygen's family, or group 16, have 6 valence electrons, which means they traditionally will form a -2 anion in order to achieve the octet rule. Like the alkaline earth metals, these are moderately reactive because they are 2 away from achieving that ideal number. The halogens are group 17. They contain 7 valence electrons, and because they are 1 away from that ideal number of 8, they are very reactive. They are just as reactive as the alkali metals. However, they will do so in slightly different ways. Halogens will take -1 anions when they take their ion form. This is very common in many salts. Also, if you manage to find a halogen in nature, you'll find they occur in a diatomic form, which means that if a chlorine atom will bond to a fellow chlorine atom. By doing so, this helps to stabilize them. However, do not be fooled, they are still very reactive. Group 18 are known as the noble gases. The noble gases, with the exception of helium, have 8 valence electrons. Helium only has 2, only because it is very small. However, all of them are exceptionally stable. They have a full set of valence electrons, regardless of what their size is. Therefore, they do not traditionally form ions, nor do they traditionally bond. The only noble gas that has been shown to possibly form bonds is xenon, and it only has done so under certain lab situations and only with fluorine. Groups 3 through 12, also known as the D block, are the transition metals. They transition you from part of the main groups, the alkali metals and the alkaline earth metals, to the other part of the main group elements, groups 13 through 18. The valence shells here contain d electrons, and so it is difficult to discuss how many valence electrons these metals have. The answer for how many valence electrons will vary depending upon how it chooses to act. Do the d electrons count, or do they not? Depends on the situation. Therefore, valence electrons are traditionally not discussed for transition metals. All transition metals are not perfect, but good examples of metals. They are shiny, they are conductive, and they are malleable, especially those that are the jewelry metals like silver or gold. But this is true for almost all of the transition metals. Because of the varying number of electrons involved, especially because we have more than one family we are discussing, the reactivity here varies. However, the notable thing is that all the members of the transition metals are less reactive than those found in the main groups. Many of these can be found in nature. For example, you have seen silver and gold. You've also seen iron. These are all transition metals. The lanthanides and actinides, the 2 rows that are at the bottom of the periodic tables, are collectively sometimes referred to as the rare earth metals or inner transition metals. They are the members of the F block. Their electron configurations contain F electrons, and as electrons are added, they go into F orbitals. Because of the fact that they have the F electrons, they have very similar chemistry to the transition metals in terms of their reactivity and also the difficulty discussing how many valence electrons they have. Valence electrons are traditionally not discussed for lanthanides and actinides because there is debate about how many there will be. And a fun fact to know here, all the members of the actinides are radioactive. So why learn about the periodic table? The periodic table is an exceptionally useful tool to us. There are numerous chemical and physical properties that repeat as you go through or that have other predictable patterns. This generally is known as periodic law. There are properties that repeat in a periodic fashion. The trends in the periodic table are in fact so powerful that they can be used to make predictions about undiscovered elements. For example, at the time when Mendeleev first created his periodic table, the element gallium had not yet been discovered. Gallium is a member of aluminum's family, and since boron and aluminum had already been discovered, he was able to make a guess at what gallium's properties would be, and he was very close to correct. For example, he predicted the density of gallium with only an error in the 1,000th or 3rd decimal place for the density. And so, the periodic table is a very useful tool for all chemists.